Uh, Hello, everyone. So in this lecture, I'll be explaining which is called the Lagrange theorem, which is has to do with the sizes of subgroups. And I'll explain it later on. And then we go, like using Lagrange theorem, we will be able to prove like Euler's theorem, which is the general case of also Fermat's little theorem. So we prove all of these three together today. Uh, so we begin from the last time. Uh, So the definitions of the coset. Just to review it, so a coset, if you multiply all the elements here by some element A, in X, or X belongs to H, where H is a subgroup of J. So basically this was the definition of the coset. Then we can go to Lagrange theorem, so which says like we have a subgroup, so H is a subgroup of G. Then we have the order of the subgroup H. We have to divide the order of the group G. So let's see in the case of the 15 here. So H was a subgroup. So this was our H, which is a subgroup. And this was the full group, which has 8 elements, and this has 4. So it's indeed the size here of this group divides the size of, the size of the subgroup divides the size of the whole group. So in order to prove this, we have to prove a few points first. So the first one, so it says like if we have all the cosets here of H, so all the cosets are either the same or disjoint. So I mean any pair of cosets, they're either the same thing or they don't share any elements. As we could also see in the same example here. So here we had this coset, so it was the same. So they share all the elements or they don't share anything as this and this. So in order to prove this, we have to start by showing, so we say, for example, we have two cosets, AH and BH, and they share some element. So let's say there's AX equal BY, where X and Y, they both belong to H. Means we got some elements X and Y from H, and we multiply the first by A and the second by B. So this part, so this like belongs to this set and this belongs to this set. And this, so this is one of the shared elements between both of those. So you have to prove that both will be equal in that case. So the way we show this, we can rearrange this expression by multiplying here by the inverse and here y is inverse. So here we can see that x and y are in H. So by the closure property, we have also xy belong, x inverse belongs to H, and hence also the product using the operator also belongs to H. So we also have that the inverse times A belongs to H. So using this, you can we can have here that if there's some element belongs to here, let's call it Z, equal, so let's call it G, is equal to AZ, and that belongs to H. So do the other way around. So here, yeah, maybe we took this in the bad order. So this could also be, from here we can derive that. So x times y inverse is the same as A inverse times B. So this would help us a bit more, but like it doesn't matter. So also, and this also A inverse B belongs to H, using the same reasoning here. So here if we have an element G, which belongs to AH, so we can write it as something like that for some Z in H. Then we can write this Z as like A inverse times B for some Z2. Where Z2 is also an H. So we can use this number basically as a substitution here. So A inverse is B Z2. So the way we can get this Z2 is basically by multiplying like Z times this inverse, the inverse of this part here. So this will give us the Z2 we want. So here the G, we can substitute this Z by this expression, and we get this part, which is equal to BZ2. And here we know that the Z2 also belongs to H, so basically the G will also belong to BH. Can show it that way. So G belongs to AH, means that G is equal to AZ. Means that so as you can see, this is all the identity element. So it's the same what I wrote earlier, but just reordered. So the Z here has to belong to H by the definition here. And then, so this, as we proved earlier, that both of these belong to H, so this product belongs to H. And this part we can, it's equal to this. Equal B, call it W, where W belongs to H. So we get that. So this implies that J belongs to BH. So basically this proves that AH is a subset of BH. And we can repeat the same procedure without any loss of generality. We can swap the B and A. We will also be able to prove that BH is a subset of AH. So it means they're equal. So we could prove this under the assumption that there was an element shared between them. As we said here, so there's an element that belongs to both sets. So if there's an intersection, then they have to be the same, or if there's no intersection, then they are disjoint. So this proves the first claim that so all the cosets are either the same, like any pair of cosets, either the same or disjoint. So this is the first claim. So the second would be that all cosets have the same size. So this we prove by making a bijection function. Like if you don't know what a bijection is, so basically it's like just a one-to-one function. So if we have some elements here, so this is a bijection. So it has to match each element to exactly one element. And we can't have something empty here, so something like that, or so this first function is bijective because it matches every element here to exactly one element here, and also it goes both ways. But here it's not bijective because there's an element here that was matched by two different elements from the input. So we can't, this is not a bijection because the bijection means we can also make the inverse of that. So, but the inverse here is not defined because we have two possible outputs. And here, we also don't have a bijection because this element doesn't even have an inverse. So this is not defined. So basically the bijection will happen only if the two sets are having the same size and each element somehow ever corresponding to exactly an element from the other side. So here we construct this bijection from AH VA. It's defined like this. We get an element X. We make this part here and there. So here X belongs to X is equal to AZ because and Z belongs to H because X belongs to AH. Then this f of X will belong to BH because this part will belong to X, will belong to H, and then inverse. This is basically So it means like for each element in AH, we could find an element in BH to assign it to. So we could make this assignment from here, but we also have to make it from the inverse direction. So the other function that would be actually the same, so it's the inverse of this, would be the bijection. So it would be the function in the other direction. So if inverse of x would be x b inverse times a. So this will map every element from BH to AH. So here we could find that we could map each element from like the first set, so the AH, to an element in BH, and the opposite, so it means that they are, so this is a bijection and both sets have the same sign. So the size here is equal to the same size here. So from here, this we will take this assumption. So to prove Lagrange theorem, we revise some few points we proved. Yeah, there's a trivial point, probably I didn't prove that. So each element in the supergroup G will belong to one of the cosets. So basically, it will belong to the coset AH at least, because H is a subgroup, so H has the identity element E, and basically AE is A itself, and this belongs to this coset, so the A belongs to some coset, so this one. So it could be even more effective. So using those three parts, so first, like, A belongs to H, then it belongs to some coset called the curved H. We say there's some coset, let's say C H. So if A belongs to G, then it means that A belongs to some coset in H. And like this curved H is like all the cosets we have. We also have like, so the cosets are all like intersecting or disjoint. If we have two cosets here, AH and BH, then either AH is equal to BH, or AH intersection BH is empty. Like if we look at those two properties alone, it means that if we have, let's say so this is the set G. So every element in it has to be in some coset. And all the cosets are either like, so disjoint or the same, so it means like the cosets are making some partitioning like that. where each coset doesn't intersect with any coset, any other one, and also like all the cosets cover all the elements. So this we get from this will prove that we partition G by H. So it means all of these different cosets, if we add the sum, like the sizes of them should be equal to the size of the subgroups. Let's say X belongs to so this is one of the cosets. So the summation of the sizes equal to this, the size of the supergroup G. And the last part is important. So we have that that all the cosets have the same size, because we could find a bijection from any pair of cosets. So basically it means that the cardinality of any coset X is equal to some constant K for all X. Here it means that we can substitute this part here to get something like that. K for each coset. So basically, so K times the number of different cosets is equal to G. And here we have one of the cosets is EH, which is the same elements as H itself. So basically this this part here is equal to absolute, to the cardinality of the set H. Here, as you can see from all of these, we proved that so the size of the cosets, so this is the number of distinct cosets, and here the size of the subgroup H is equal to the size of the subgroup. So number of distinct cosets. So it's the order. Yeah. The subgroup H. And this is the order of the main group G. So as we can see here, that G is actually divisible by H from this equation, which is exactly the Lagrange theorem. So the size of the subgroup divides the main group. Basically, this is Lagrange theorem, and you could already see it here in our example. So here we have two exactly distinct cosets. So this one, so this one and this one, the 7H, for example, and the H. So these two are the only two distinct cosets, and so there are two, and the size of each of them is 4. They all, as we see, they have the same size. So 2 times 4 is equal to 8, which is the size of the multiplicative group here. we have. So this shows how the theorem works. So from this, we proved Lagrange's theorem. From that, so the Euler's theorem follows relatively easily. So as we said before, so there's so if we have an element A, which is so it's co-prime with some given number n. So A and n are co-primes, so A is in this multiplicative group modulo n. So it's the set of all numbers that are co-prime with the n. So here, if we take this, the elements generated by A, basically A0, A1, and so on. So it's the powers of all the elements. And as we can see, so the powers are, they form a subgroup, as we stated earlier. This is because any power of A is also still exists here. So if we multiply any two different powers of A, it's still a power of A. We have AI, AJ. This would correspond to the element I plus A. So it means here that it's satisfying the closure axiom. So basically, so the elements generated by A is take the multiplication mod n. This is a subgroup of this set. So this is the multiplication mod n. So the size of this set divides the size of this set. And as we said, so here the size of this set is basically the phi of n, which is something we know by definition. So the Euler torsion function. And as we said, so we know here from the stuff we proved in the last lecture, and more definitions of group theory. And if we have this part here, so the elements generated by A, if they have the order m, then A for m is equal to the identity element. So in our case here, the identity element is 1. And we have that m divides basically 5n. So we can say that 5n is equal to k times m for some constant k. So we can make this equation to the power of k. We have mk and 1 is equal to 1. Basically, this implies the Euler theorem, a to the power 5m, because here we can just substitute this for this formula here. So this is equal to 1. And here the operator that we use, that is multiplication remainder n. So basically, we could also say this in a different way, that a to the power 5n is congruent to 1 mod n. If a and n are coprimes, because if a is not a coprime, then it doesn't even belong to the set that we have here. So because of this assumption, we have the a belongs here. Otherwise, we couldn't use this derivation. So basically, this proves the Euler's theorem. And from this, we could also prove Fermat's little theorem. I think I did earlier somewhere. So Fermat's little theorem says, so the 5p, which is the numbers that are coprimes with p, is basically equal to p minus 1. Because p is a prime number, we have all the numbers from 1 until p minus 1. They're all coprimes with p. Basically, that's the size, and so we get as a special case of Euler's theorem that e to the power p minus 1 is congruent to 1 of p. So basically, this was it for today. So this was a proof of Lagrange's theorem in good theory and how we used it to prove Euler's theorem and Fermat's little theorem. So thanks for listening.